Yes, I'm beginning.
Okay. So, good afternoon, everybody. My name is Amit, and I'm the director of AI here at Mellanox, leading the AI group within the company. And today I'm going to talk to you about something that is not directly related to the work we do at within Mellanox, but it nonetheless very, very interesting. It mostly deals with something very unique that happened in the field of natural language and in AI in general in the past few 2-3 months. And so we'll discuss this in detail, and in general, I want today to discuss in a very high level and trying to be as less technical as possible, how computers understand language, what methods we used to have, what methods we use today, and what might be the future of language understanding, and does the current state of the art of language understanding means that computer can think or are on their way to be able to achieve this. So something interesting, a very famous writer, Neil Gaiman, he posted a story called I think Chrysalis, if you say the word like this, a very interesting story. You can read it. I came out of the cocoon naked. The chrysalis is lying there empty. My family and the doctors and the nurses all gasp and say, "You're beautiful." I am, of course. The transformation is complete. I am beautiful. I have perfect golden eyes, 6 arms and wings like butterfly wings, iridescent and blue. I am slim, I'm tall, I am an angel. And this story goes on, and I can tell you that I read it, and it's a very good story. It's a short story, but it's a very good one. The Satan comes at some stage, and there is some debate between heaven and hell. Very, very interesting. So this is one example. Another example, some news articles that I read about the some church in the US, I think, or in Britain, that they opposed gay marriage, and this has caused some historical split between the two. Between the church to two different, I would say, churches, and you can take a minute, read this as well. So if I just came out and asked you, who wrote this article? Who wrote this story? Did Neil Gaiman really wrote this story? Did the news reporter really wrote this piece of a news article? I think most of you would have a very hard time to know that not a human wrote this. In fact, both pieces were written by a computer without any supervision, without any editing, completely written by an AI. And when there was a poll on this kind of articles, 88% of people that were asked who wrote these pieces said a human wrote this and not an AI. And this is a very big breakthrough, because up until I think a year ago, most pieces, at least long pieces that were written by AI, we could spot this very easily. They were not very coherent, they had repetitions, they lost their line of thought, and this is the first time ever that very long pieces of writings were made by a computer and were completely indistinguishable from something that a human would write. So what actually happened here? As you know, some of you know, Elon Musk started a company called OpenAI, which was supposed to be an AI company that was a non-profit company. But after a few years, he had to leave her. And about a year ago, Microsoft decided to invest $1 billion in OpenAI. They didn't buy them, but they invested quite a lot of money compared to the value of OpenAI. And it raised some, let's say, eyebrows on what is Microsoft going to do with OpenAI, because OpenAI didn't have any sort of commercial product. They were a non-profit company before, and it was unclear what are they going to do with this big amount of money. And then on April 2020, it was announced that Microsoft and OpenAI teamed up to build a very, very, very big AI supercomputer. In fact, the biggest AI supercomputer to that date, and the fifth biggest supercomputer in general. So this was the first result that we saw of this investment. And by the way, the supercomputer uses NVIDIA and Mellanox hardware. And I know at least some of the people that were involved in this project. So definitely a local pride. But then the question that was raised was, what are they going to do with such a monstrous supercomputer? And the answer was that they're going to build the biggest language model ever made. And this language model is the one that created both of the articles that we seen before. But before we dive into what it can do, the first question you may ask, what is actually a language model? And this is what I'm going to talk in the next 10 to 15 minutes. So we understood OpenAI built the largest language model ever made with 175 billion parameters. But what is language model used for, and what it is at all? So according to Wikipedia, a language model is just a statistical way of a statistical language model is a probability distribution over sequence of words. What does it mean? In simple words, what we want to have is to understand what are the chances of a given word sequence in a given language. Like if you give me a sentence, I want to know, does this sentence make sense in this current language? Does this sentence is something that someone might say? And why do I need this? Because I want to be able to understand language. If I understand just know words are by themselves are sometimes meaningless. But when you starting to connect words, you can start to understand and generate language. So language models are a computational way to understand and generate language. Let's take a look at this very simple example here. So we have a sentence, can you please come? And we want the computer to be able to understand that the next word should be here. So the computer gets some history of words, and we want it to predict the next word, and we want it to be as accurate as possible. This way, the computer understands and is able to generate a meaningful sequence of words. The simplest way to do it, to build this kind of language model, is called the unigram way. So remember, we need to understand if a certain sequence of words makes sense. So the simplest way to do it is just to understand if any of the words has any chance to appear. So what we do, we take a very big corpus. It can be Wikipedia, it can be thousands of books, and we just count every word in this sequence. And then we normalize by the total number of words, and what we get is we get a number between 0 and 1 for every word, which means what is the probability of this word in this language. And this brings us some sort of statistical distribution over a sequence of words. What the problem with it is that there's no context, because every word is counted independently. There is no context. And on this example, when we ask the computer to complete the last word, what it would do, it would just take the word that has the highest probability. It might be I or has or something like a word that appear a lot in the text, and it would not mean anything because it is not related to the context. It is not related to the sequence of words. So the next thing that you can do is not to count every word by itself, but to count pair of words. You want to start to understand some sort of a sequence of words. So what you do, you take again this big corpus and you count every possible pair of words that appear. And then, for example, in this this example, when the computer would see come, it would see that the pair of words that has the highest percentage is come here. And then it would probably complete the word here. But you can already imagine that just counting every pair of words might not be enough, because there are sequences of 3 or 4 words that we need to understand in order to make sense. So the longer the context we need, the larger gram that we need. So we can do it 2 grams, we can do 3 grams, we can do all the way to 10 or 100 grams. So for example, in the 10 grams, you count every possible combination of 10 words within the text, give it a number, and then you can try to understand and generate language and predict what would be the next word. So the main problem with it is that the longer the text we have, the more words we have, and n-grams grow exponentially. Okay, just imagine that for 2 grams, we have 2 by n by 2 possible pairs, because for each word we can pair every other word, and we need to count it. For 3 grams, it's n by 3, and so on and so forth. So it's not really feasible. If we want to be able to understand long sequences, if we want to be able to understand the meaning of the word and be able to generate a language, the n-gram presentation is probably useless unless it's a very, very small and dedicated text. So natural language researchers decided to go another way. And based on some, let's say, assumption that was stated by Firth, a very known language researcher, who said, you shall know a word by the company it keeps, they decided that the best way to understand a word is to understand it by its context. So if we have a computer, the computer needs some numerical representation of the words. Eventually, a computer is a numerical machine. It can't work with words, so we need to find some sort of a numerical representations. And as we said, context equals meaning according to this hypothesis. So the first and maybe most simple way to have a numerical representation of the word is called account-based representation, which means that if I have a text, and it can be as long as we want, but this one in this example is quite short. For each word in the text, we count which other words appeared next to it. Because as we said, context equals meaning. So we build on this, that the words that appear next to the word we are trying to represent will eventually represent the meaning of the word. So in this example, we have the entire vocabulary we have is I like, enjoy, deep learning, NLP, flying, and a dot. And for each of these words, we count, like I is appearing near like 2 times, and near enjoy one time, and the word likes appear near I 2 times, and near deep 1 time, and near NLP 1 time. And then we have a vector now, and this vector now represents the word I in this corpus, a very small corpus that we built. And you can imagine maybe that if we take a very large corpus, then these vectors would become more and more dense and would start to have some sort of a meaning. If you look at them, and maybe I would not even tell you what words this vector represent just by the words that they appear next to, you can maybe try to guess what would be the word. For example, if I would say a number, you would probably see a lot of numbers that appear next to him. Or maybe when I would say a car, you'd see the words engine, the word drives, the word wheels, and you might be able to understand what is the vector representing. So this is the most simple way to get a word to be represented by its context. The main problem is that it's very, very sparse and it's high dimensional because the dimension of the vector depends on the number of words in the vocabulary. So if, for example, in English, most big corpuses have between 10,000 to 50,000 unique words, and we're not even counting things like signs, like question mark, dots, and stuff like this. So we have a vector with 50,000 coordinates. And you can imagine that if we want a computer model to actually use this kind of vectors, the computation it takes would be very, very large. The other issue that we have with this vector is that they are still very sparse. What do I mean by this? Is that most of the entries within the vector would be 0 or very close to 0, because you can imagine that not every word appears next to any other words. Most words have a subset of words that they usually appear next to, and they do not appear near any of the other words. Like if we take, for example, the word car and the word cucumber, they would probably never appear next to each other. And this is true for many, many examples. And usually when we do machine learning and when we do, even in general, we deal with numerical representations. If the representations are very sparse, this is something that is not useful because we need a lot of memory to save something that is basically empty for the most of it. So at about 2013, some students from the University of Toronto invented some sort of a model. It's not a deep learning model, though some people think that it's a deep learning. It's a shallow model. And this shallow model have a task. The task is that they give him a sequence of words, like you can see, a word at t-2, a word at t-1, and a word at t+1, and a word at t+2. And they want the model to predict the missing word. So we have the words that came before the missing word, the word that came after the missing word, and we want to predict the missing word. Here again, you can see that meaning equals context. The model gets the context of the word and is trying to predict which word best fits in this context. So here again, we are trying to get a numerical representation, a meaning of the word by looking at the context. So this model, we take a very, very big corpus for this model. We can take Wikipedia, a lot of things that we can do. And then for each sentence, we remove some of the words, leave just the context, and make the model try to predict what is the word. And we train it. And then we have here this embeddings layer. This is something that is initiated randomly. And as we go along and train the model to be able to predict the correct word, this kind of embedding layers is starting to get unique numbers for each word. So every word in the context is getting a representation in this embedding layer. And each of these embedding is now small. It does not depend on the vocabulary size that we have. It only depends on the model. So it's quite small, between 100 coordinates and 2000 maybe, and it's dense. It means that all of the numbers within the embedding layers are some numbers between 0 and 1, but mostly they are something meaningful above 0. So these are much better representations because a model now, we don't need tons of memory to save a language model, to save this kind of embeddings, and they are not sparse and they can be used in other models. So after we train this model, eventually what we get is we get a numerical representation of every word in the corpus that we used. And if the corpus is big enough, we might assume that we get a good numerical representation of every word in the given language. For example, here in English, we get a good representation, and then we can use it. The computer, which needs a numerical representation of words, can now use those embeddings, those numerical vector of words, in order to understand and use them to understand and generate language. And this indeed proved to be very successful, and the most interesting is that it fulfills what we wanted. We wanted the numerical representations of words. We want words with the same meaning to have vectors, to have numerical representations which are pretty close to each other. So we can see here in this example, things that belong to maybe housekeeping, or maybe to gardening, or maybe to the kitchen. They all have vectors, numerical representations, which are pretty close to each other, which makes sense because they have similar meanings or similar context that they would appear. They also have some very interesting characteristics in terms of linear relations. For example, the linear relation between Turkey and its capital is exactly the same between Canada and its capital and for a lot more countries. And this is something that appears a lot in the text. So the relation between words is something that is similar. We have similar relations between vectors where we have similar relations between words. So for example, and it's a very famous example, if we take the vector of a king and minus the vector of a man, we get exactly the same vector if we take the vector of a queen and subtract the vector of a woman. So this is something very interesting, and this did lead a lot of NLP researchers to think that here we do have finally some sort of representation that actually captures a lot of the meaning of the word. And this led to a very big rise in the use of deep learning for natural language processing, because now that we have this kind of numerical representations, these dense embeddings, we can use neural networks to do many tasks in a very easy way. Whether before we had to do a lot of very sophisticated pre-processing, like the counter-based model, and then start doing some very expensive modeling. Here, it all became much simpler, and unsurprisingly, the amount of deep learning papers in each of the biggest NLP conferences has risen dramatically. You can see here, 2013, the Word2Vec, and you can see the dramatic increase from about 35% of papers on deep learning on average to about 70, and I can tell you today that the numbers reaches about 90 to 95%. So most works in NLP today are based on deep learning, and this is something that is heavily related to the fact that we were able to create this Word2Vec model. And we got very good results. I give just two examples. A very famous paper which used a very simple neural network and was able to achieve amazing results on many NLP tests, like sentiment classification, which you need to decide if a sentence is positive or negative, or if a rating is good or bad. And this was a very unique paper because it showed that with a very simple model, if you use a good vector embeddings, you can get great results. Another big breakthrough that happened around 2016 is that Google replaced their old Google Translate engine with the new one, and it was dramatically better, to the point that on some languages you can't really know that it was a computer that generated the translation. Probably most of you remember it. It was a very big breakthrough, and it was also based on the fact that we moved from classic language models and classic word understanding to word vectors or word embeddings, and started to use NLP. So this is something that happened, started around 6 years ago, and led to a lot of successful results, and to the fact that the deep learning revolution caught with NLP as well, after she proved itself quite significantly in the field of vision. So what was the next step? And this is something that happened not long ago, about 2 years ago. So we talked until now about embeddings. Yes, so we have a vector embeddings, and embeddings. These embeddings are capturing to some extent the context, so they have some sort of a meaning of a word. But we have an issue. Let's take this for example. We have these two sentences. The bank will not be accepting cash on Saturdays. And the second one, the river overflowed the bank. Obviously, the word bank is the same, but the meaning is completely different. So we can't use the same embeddings for these words because it represents a completely different word. And in the previous models that we have, in the word embeddings, regular word embeddings models that we showed so far, these two instances of the word bank would have exactly the same numerical representation. Obviously, this makes the computer work and to understand the language much harder because these words, where they appear in different contexts, they have different meaning. This led to what is called a language model. A language model means that we are now creating a different embeddings for each context. So we're not using the same embeddings for each word. The embedding depends on the context that the word appears. So if we have 10,000 sentences where one word appeared in the corpus that we use, we will have 10,000 embeddings. So how is this done in this word called Elmo? I think it was published by Google. So the language model, as we said, the language model role is to try and predict words, given a sequence of words, predict the next word. So the language model here is getting a sentence, and is doing two tasks in parallel. The first one is to try to predict the next word given previous word, and the second is trying to predict past words by getting the end of the sentence. And then what we do is we combine the internal representation of words that the model used of the forward task and the backward task along with some sort of initial embedding, which can be the embeddings that we use so far, the embedding we showed, the word-to-vec embeddings. They are all combined together in some sort of a function or a concatenation, and we get now a new embedding which is completely context dependent. So the happy embedding, the embeddings, the numerical representation of the word happy here will depend on the fact that it appeared within the sentence the cat is happy. And if we have other sentence, then we have another embeddings. This allows the model to have embeddings which actually take into account the context. And then when we have similar words with completely different meaning which depend on the context, we are finally able to get different numerical representations. And this indeed proved to be very, very useful and very good. And you can see some result. The Elmo model improved the state-of-the-art results very significantly. And in fact, this is much more similar to how we as humans perceive language. If you say something to me, if I just hear one word, I would probably don't even know what you mean. I need the context because the context means a lot on what your words mean. So these pre-trained language models became the new state-of-the-art, and Sebastian Ruder, which is a very famous NLP researcher, he predicted in 2018 that it's very likely that in a year time NLP practitioners will download pre-trained language models, which is the Elmo. Elmo is a language model because it predicts the next word. This is its role, rather than a pre-trained word embeddings. Word embeddings, I remind you, this is what we saw earlier in the word-to-vec work that was done, and he was completely right, by the way. In most NLP tasks today, people use pre-trained language models instead of pre-trained word embeddings. So now we answered the question we had about 10 minutes ago. What is a language model and why we need it to understand language? So a language model is a model that is trained to predict the next word given a sequence of words. And its internal representation are the meaning of the words that this model learned. And we can use these internal representations as the meaning that the computer captured for this word and then continue with them to a lot of other tasks and achieve, as we see, very good results. So we talked a bit about the past and how we got here to talk about language models. And this is now what we use in order to understand and create a significant numerical meaning of words. Another big breakthrough that happened again about a year and a half, 2 years ago, was the invention of transformers. Transformers started from a very famous paper. Now it's very famous, called Attention is All You Need. And what transformers mean, I won't get into the details because there are a lot. I do want to discuss what are the what is new here and why it's very important for computers, why it helped computers to understand language better. So in the past, language models were built with a neural network called LSTM. LSTM, what it does eventually is that it takes a sequence of words and is processing the word step by step. So each time it just sees the previous word and trying to understand what would be the next word. So for example, here in the translation example, so when we have an input sentence, we want to translate it to French. The computer needs to translate it to French. When we're starting the translation, the computer in fact only sees the word student. It does not see the entire sentence. I would say though that the LSTM does have a sort of an internal memory that is trying to remember the important words from the form. So this is something that did work quite well, but had a lot of issues because the model need to remember a lot of passwords. It doesn't always know what would be the most important words to remember because different tasks might require a memory of different words. And another main problem was that the longer the sequences got, if we had here not this sequence of 4 words, if we had a sequence of 20 or 30 words that we wanted to translate, the model fails to capture such long-term dependencies. And this is why LSTM was very good, but not good enough. So the first solution that was offered is to use what we called an attention mechanism. Attention mechanism means that when we do the decoding, when we do the actual task of, for example, of translation, we are able to look not just on the last words and hope that the neural network will remember the important stuff from previous words. We are able to do some weighted average look on the entire sequence. This helps us a lot in terms of memory because now we don't need to memorize which words are important because at every step we can look at all of them. But there were still two main issues with the LSTM approach. First one is that it was still very slow. As I said, the neural network is processing one word at a time, which you can imagine if we need to process a lot of words, this is very slow. And there were a lot of other issues that we won't get into. So in 2018, late 2018, the transformer architecture came into the world. And the main idea of the transformer was that we are now processing not the word one at a time, we are processing all the words in parallel, together. And this solves two issues. The first one is that we can do a parallelization. The model now is not serial, it's parallel, so the computation here is much, much faster, which allows us to bigger and bigger models and still train them pretty fast. And we can still use attention. Another unique thing here is that now, instead of using regular attention, we use what it called self-attention, which means that whenever we process a word in the sentence, we are looking with some weight on other words in the sentence, because as we said, the meaning of the word depends highly on the context of the word. So we need to give some attention. If we take this example, the animal did not cross the street because it was too tired. What it means, what it refers to, what is the animal, is it the street? So the model here is doing what is called the self-attention. When it looks at the word it itself is referring him to other parts of the sentence that would help him understand better what it refers to. So we have parallel processing of words, we have self-attention, and finally, because the order of the words is very meaningful, and here, remember, since we don't process the words one at a time, the order of the words might be completely lost. And as we all know, the order of the words in the sentence is very important for the meaning of the word. So we have, what is called positional embedding. We have another information that is added to the model that is called a positional embedding. And these three things together allowed for a very big breakthrough in terms of language understanding, because we can now build much bigger models which parallel a lot, which process a lot of words together. And by the way, it's also more similar to how we do, because when we read text, we never read just one word at a time. We read a sequence of words, and we usually keep some length of sequence in our head always. So when we try to understand a word, we have this sequence of words in our head and not just the last word or the last two words. And also, whenever we look at a word, our mind is referring itself to other words in the sequence to understand what the words actually means. So these transformers led us even closer to having the computer understand language the same way that humans do. And this started from the translation task, but it became the new standard for language models in general. So these are transformers. There are many famous transformers like BERT, Megatron, and GPT. GPT is a transformer language model. So we understood what a language model is. Now we understand what a transformer is. And now we go inside GPT-3. GPT-3. So GPT-3 is the latest model that was released by OpenAI. And when it is trained, it's trained on a very simple way. It's a language model. So what we do, given an initial text, just predict the next word. And then the next and the next, up to a window of a sequence length of 2048 words, which is quite long. It's the longest that any language model was able to do this far. But the basic mechanism is very simple. Predict the next word. And as I said, we do it in parallel because this is a transformer. Notice though, the GPT only used the decoder part of the transformer and not the encoder part. And if you want to see very simple to understand illustrations, you can refer to one of the links that is shown here or in the previous slide. But basically, this is GPT-3. So what makes it so unique and what made it achieve such good results in so many tasks? So for this, we need to have some numbers. GPT-3 has 175 billion parameters. This is 10 times bigger than the biggest language model that we had previously, which was Microsoft NLG Turing model, and it is 100 times bigger than the previous GPT-2, which was only a year ago. And notice that a human brain is 100 trillion parameters. So in that sense, GPT-3 is now not very far from a human brain in terms of size. This is a huge size. You need 300 gigabytes just to keep this model on your memory. And this is something that was never seen before in the world of deep learning and neural networks in general. The next one is this model was trained on the largest text dataset ever created. The dataset contains about 500 billion tokens, which translate to about 1 trillion words. basically the entire text in the internet. It just took all the website, all the code, all Wikipedia, CNN, whatever you want, and just trained on it with the goal. Remember, it is given a sequence of words and need to predict the next words. And the data set itself is 20 times bigger than the data set that was used to train GPT-2. So 100 times in size, 20 times bigger in terms of the text that it was trained on. And as I said, this is a huge model, and someone calculated that it probably took about $5 million just to train one instance of this model. This is just on electricity. We're not even talking about a supercomputer, the cost of the supercomputer just on electricity. It took about $5 million just to train the model. And about if we use just one GPU, and obviously as we saw, they did not use one, they used tens of thousands of GPU. But if we used just one GPU to train the model, it would take about 355 years to train GPT-3. So as you understood by now, GPT-3 is very big. And surprisingly, because it's so big, it is able to achieve very good results. And the very good results come mainly in the field of what we call few-shot learning. What do I mean by this? In previous approaches, if we had some sort of natural language task, we had to train a language model. To pre-train it, as we discussed before, you can take a large corpus and pre-train the model and have some sort of embeddings that you have. And then you need to fine-tune the model for the task. So if it's translation, if it's question answering, if it's sentiment analysis, you need to have thousands of examples that you now feed the model, the pre-trained language model, in order to do the task at hand. The problem is that we humans deal with thousands, if not millions, of LNP tasks naturally. And if we wanted a model to be able to do all these tasks, we need to train it with thousands of examples for each one of these millions of tasks, and it's just infeasible because a lot of the tests doesn't even have a lot of labeled data. And what amazing about GPT is GPT-3 is able to achieve great performance on practically infinite number of tasks with just very few examples, and we're talking about less than 100 examples for each task. So how does it work exactly? And I think this resembles how we as human, because if I give some of you a task, an NLP task, I would probably have to show you up to, I don't know, 10, 15 examples, and you would probably catch the task and do it pretty good. And for GPT-3, this is one of the biggest, I think, advantages, that it is able to learn new NLP tasks with just few examples. This is something that was unseen before. Keep in mind, it does not achieve the best results comparing to models that were fine-tuned for this specific task, but it is able to achieve very good results with a minimal number of examples. And what is more surprising, that size matters. The fact that the model is able to achieve such good performance on such human-like performance on so many tasks is because it's that big. And this was a very big surprise, because some people thought that it would take a completely different approach to achieve such performance, but OpenAI showed that sometimes size matters. So how people use GPT-3? So basically, what you can do, you can go with 3 ways. First one is ask GPT to do a task without giving him any example, and hope that it was trained on something similar, and this works quite well for a lot of tasks, for example, for translation. You can do one shot, which means you give just one example to the model and expect him to continue from there, and you can do few shot. You can give him several examples. As we said, you need to give him up to 100 examples, and then it is able to learn the tasks. So how does it work? We have a very long pre-training phase, and then we are doing fine-tuning with very few examples, which makes the model slightly better for this specific task. But the fact that we are able to get good results with this model with so little tasks, with so little examples, open a huge amount of possibilities on how to use this model, as we'll see just now. But this is in general how GPT, so GPT is a very, very, very big language model, meaning it was trained to predict next word. The architecture is a transformer, which we discussed its unique features a few minutes ago. And the most important part of it is its ability to fine-tune and achieve good results on specific tasks with just few examples. And as I said, which resembles how we as humans do it much more than we had so far with other language models. So let's see a few examples of what we can do. So we already saw in the beginning of the lecture 2 examples of creative fiction that the model created. It created a Neil Gaiman stories from scratch. It can create a news article. And here in this link, there are basically thousands of examples, amazing examples of creative art, creative writing of GPT-3 with, as I said, very, very long texts that are coherent, and you would probably have very hard time to distinguish the text and see that not a human wrote this text. Few things that I liked there were a lot of humor stuff. Some occasions that the GPT-3 was able to invent a box game, complete box game with rules and history, and something very nice when it writes on the limitations of AI. And again, many, many more examples. I highly recommend you go to this link and see some of the really amazing results of GPT-3. As I said, this is something that was not seen before in any way. We can see another example. We can chat with an historical figure. What the authors here did is they took all the writings of Ayn Rand and all its interviews and stuff, they fed it into a GPT-3, and then they just created a fake interview where someone from the New York Times is interviewing Ayn Rand. This is, by the way, a very long interview. This is just a snippet. And what is really amazing is that Ayn Rand actually answers to the questions of the reporter. The reporter here is a human. He's asking question Ayn Rand. Ayn Rand obviously is dead a long time ago. And Ayn Rand actually answers very interesting and answers that actually fits very well with what she thought and what was her agenda when she was still living. So this is really amazing. And this was done with thousands of historical figures, Shakespeare and Elon Musk, which still lives, and Ernest Hemingway, and a lot more. So this is really interesting. The GPT-3 can also be very creative. For example, it was asked to write a Dr. Seuss poem on Elon Musk. And amazingly, this is also, it does remind the style of Dr. Seuss, and most of the facts here about Elon Musk are actually correct. So this is one poem about Elon Musk and his journey to conquer Mars, and it's very fun. You can read it later. And again, there's no limits to the creativity when you use such model. So here, for example, the model was trained on the Harry Potter books and on a lot of Shannon and Turing writings, and then they created a completely fake meeting between Hermione, Turing, and Shannon. And again, the results here are simply stunning. You can see here Shannon say to Hermione, "I'm sorry, I can't follow this. Magic is real." Hermione says, "Yes, it is real." Turing says, "Are you happy?" And Shannon asks, "What?" And Turing says, "Are you happy to live in the world that has not only infinite Turing patterns, but also magic and Quidditch?" And we can almost imagine Turing and Shannon, if they actually met Hermione and lived in the world but there was magic, this might be very close to what they would actually say. So this is really amazing. And as I said, there are probably tens of thousands examples like this. You can just, I think, dive just for a week or even a month, just read all these sorts of very, very interesting examples. And again, this is something that until 2 or 3 months ago were almost impossible to create or to find the computers that can generate such long, coherent, and funny, to some extent, text. Okay, so this was fun, but can GPT-3 do something useful for us? So the answer is definitely. For example, what about a fully functional fact searching engine? Let's see here the video. On this one, you can ask GPT-3 any question that you can think of, and it would answer you and give you the relevant link where you can find the answer to the question. And this is, to some extent, can replace Google, because most people just ask Google many fact questions, and you can just do it here with GPT-3, get the correct answer, get a source material to see the correct answer. So this is something really, really useful. Another student, a medical student, created a medical diagnose engine. What you see here is that the student asked GPT-3 a very elaborate and sophisticated medical question about diagnosing some 10-year-old with some sort of symptoms, and he asked him what could be, what of the few possibilities that he gave him could be the correct diagnosis for this kid. And amazingly, GPT-3 is able to not only answer correctly and give the right diagnosis, it also gives a good and meaningful explanation and a correct explanation of why he gave this sort of diagnosis. And this is something that was this on medical field is considered a very difficult question and requires a lot of medical background and reasoning, but probably because GPT-3 was trained on so much of the internet data, which probably includes a lot of medical data as well, it is able to understand the question, give the right answer, and give a correct and meaningful explanation. So, and here again, these are only two examples of many, many useful applications and examples that GPT-3 already have. What more? Can GPT-3 make my work easier? So the answer here is also definitely yes. Here you can see, for example, someone created a natural language command line interface. I would jump to the middle. To see the examples. Okay. Okay. So you can see here, I hope you hear him as well. And you can see the answers here are given by GPT-3 command line interface. And you can see that he's asking him the question completely in a natural language, and the GPT-3 is able to generate the right shell scripts in order to answer the questions that were given. See here, he corrects GPT-3, and GPT is able to understand it and correct its answer. So you saw. This goes on, and it shows many, many interesting examples. This is something just to think, if this is coming to production and really works, this is something amazing. You don't need to remember any scripts. You don't need to remember any shell command. You can just ask the CLI to do something for you, and it will do it immediately. Another nice example is here. Someone created an engine which, given a natural language description, generates a completely functioning web page of JavaScript. So you can see here, he asks for a button that looks like a watermelon, and the GPT-3 generates the correct code. See here a more elaborate example. And here again, works perfectly. And now it corrects it. So this is amazing. You can create web pages without any understanding of JavaScript, just by using natural language. So this is something that can probably help and automate a lot of the work we do. Let's see more stuff. So here we see an example of GPT creating complete Python functioning Python code. Let's hear him. So here again, and this video goes on, and it gets more and more complicated, and always the author here writes just the comment in natural language, the comment of the function, what the function needs to do, and GPT-3 generates a working and a pretty neat Python code which does exactly what the comment says. And this is, you can imagine how useful something like this can be. And there are really thousands of examples for things that GPT-3 can already do. It can create a presentation for you, write your resume, a lot of chatbots, translations, interactive text game, complete application generation from just natural text, guitar tab composer, learn from historic figures, and each day that passes, more and more cool demos of GPT-3 are adding to the internet. This is really interesting, and you can follow the site here, which is updating with really cool demos. So let's summarize GPT-3, and I would say I'm going to overdo the lecture by about 10 minutes, so you'll forgive me. If you need to go at exactly 3:30 sharps, please feel free to leave, but it's going to be very interesting. So to summarize, GPT-3 is a giant leap in natural language processing and probably in AI in general, mostly in its ability to learn new tasks just from few examples. This is something we explained a lot and saw a very good example. It is able to understand complex language structures and concepts. It is able to generate very long and coherent and creative text pieces which are relevant to the task at hand, which this is something that was almost not seen before. It is able to do very complex tasks which required massive training before or were outright impossible, and GPT-3 is able to do it with very little training, and a lot of the tasks that we saw are very complex and something that we could not imagine a language model doing this before. And it has tons of applications we would probably see in the next few years when GPT-3 is made commercial. However, it is not an artificial general intelligence. It is not a human-like computer, and by most researchers, not even a step towards it. So it's very impressive, but it's not an AGI. And in the next 5 to 10 minutes, we'll see why and what we might be able to do in order to advance further into this. So let's talk about GPT-3 limitations. First of all, GPT-3 fails a lot in tasks that require actually a scene or a world understanding. Let's take this as example. John entered the living room. John put down the candle and picked up the eggs. He went to the great hall. He dropped the eggs. He then entered the kitchen. So where is John now? He's in the kitchen. That's okay. Where is the candle? The candle is in the living room. As we said, John entered the living room and put down the candle. This is correct. Where did John find the X? He found it in the great hall. This is not correct. He picked the great hall in the X in the living room. Where is the X now? In the kitchen. This is also not correct. Where is John? What is John holding now? The candle. But we just said that the candle is in the great hall, so obviously John is not holding the candle. So this is something that for us, even for kids, is very, very simple to understand. We imagine the house, we imagine the rooms that John goes to, we imagine what he picks up, what he leaves, and we are able to answer this question almost immediately by looking at the text. This is a very easy task for us. GPT-3 fails completely on these kinds of tasks almost always. So this is something critical. Language models are still unable to really understand the world. They're not really able to understand something that is beyond words. Another thing that they fails, most language models fails pretty much everywhere, is arithmetic. For example, here we say which numbers come before 10. It says 9. Which numbers come before 100? 99. Which number comes before 10,000? And GPT answers 9,099, which is not correct. And if we increase this to 1,000,000, you can see that it always says some number and 99. Because when arithmetics in language models start to have bigger numbers, like 5 digits or more, language models are completely, and deep learning in general, by the way, is completely unable to do simple arithmetic operations. Another major problem of any language models is that they are as good as the data they are trained on. And obviously, if we tell them to just generate text, they would generate a lot of racist and biased text because these are the texts that are found within them. So for example, here someone took GPT-3 to generate tweets, and you can see a lot of tweets that GPT-3 generated are very offensive. Jews don't read Mein Kampf, they write it, black is to white, as down is to up. The best female startup founders are named girl. Most European countries used to have approximately 90% Jews, perhaps they have recovered. And a lot of very offensive and very racist tweets. And by the way, it's not the first time. Almost every time any company uses some AI to generate tweets, very fast it's starting to generate racist and biased tweets. So these are failures, and these problems, and unfortunately many more, are relevant to almost all language models that we use today. And from another aspect, why language model is still not an AGI? So many examples show that language model fails when it comes to semantic understanding, causal reasoning, which humans are very good at. Just the examples we saw before about John traveling in the house, picking stuff and dropping stuff. This is something that language models are completely unable to understand. Language model only use words, they only see words, but we as humans, we don't care about words as is. We use words as a form of communication. And there is a very large body of research, and you can see just one example here, why this distinction is so important. You can't understand language just from looking at words. You need to understand how these words are used in the real world between interactions of humans and the environment. So this is something that language models still miss. Language models still fail the task with missing or ambiguous information where human can easily succeed. You can see this in the GPT paper. They show several tasks with GPT is completely unsuccessful, and all language models are also unsuccessful on this task. And finally, humans don't learn language by memorizing trillions or billions of sentences like GPT-3 does. They interact. And you can see, and I will discuss this slideshow in a minute, but we don't learn language the same way that language models learn language, and there's a good chance that this distinctions makes the entire concept of moving from language model to AGI impossible. So what's next? What can we do in order to improve it and really get to a state where computers think and understand and create language the same way we do? So OpenAI did show that size matters. They did show that GPT-3 being 100 times larger than the previous GPT is indeed much, much, much better. So there is some thoughts that can be made that we can maybe do reach AGI by just increasing the size. If the human brain is 100 trillion parameters, what happened if we would train the language model with 100 trillion parameters? Would it be able to be the same as the human brain? This is a question that we can't answer. We would still face a lot of issues if we would have tried to do something like this. We would have hardware limitations because training such thing requires hardware that we currently don't have. It would cost hundreds of millions of dollars, if not trillions, billions of dollars, which would probably won't be effective. It would still need to use trillions of words to learn, which is not the way that we use. And finally, the given task, as we said, language model just predicts the next word. This is a major limitation that would probably, in the end, prevent this from really being an AGI. However, we might still advance this way. We'll have to wait and see. But there is maybe a different approach. A different approach would say that understanding that the word meaning is fluid and depends on many, many, many criteria, on mood, on situation, on intention, on who even says these words. For example, when I say to someone, let's meet by the dinosaur, dinosaur here doesn't mean a real dinosaur. It's a skeleton of dinosaurs that is somewhere within the places that we're meeting. So this is something that computers now are completely unable to understand. And understanding language always also requires understanding situation. Like when I tell any of you something, the situation, when I say it, is very, very important. And this situation enables me to fill a lot of gaps of things that you're not saying. For example, if I say John shot the target, and I ask the computer, did the arrow hit dead center or the bullet hit dead center? And for each of them, I'm asking, what is John holding? This is something that we as humans can answer without any problem, but computers are completely unable to understand this question. That the first one, John is holding a bow, and on the second one, John is holding a gun, because this requires the understanding of the situation. This requires understanding the world, understanding how things operate, how things interact with each other. And this is something that just from the task of completing the next word, computer would never be able to get to a level that they understand it. So few interesting directions that are being proposed in the last 2 years, and hopefully will progress. So we can try and learn language by interacting with the real world. We take some sort of a robot or an agent that is actually trying to move in actual world or in the simulation and trying to understand language by interacting with the physical world. So we can understand language by understanding situation. And this can be much better than a language model. We can also make computers invent their own language as a form of communication. As we said, words are meaningless without them being a sort of communication between two entities. So there has been some works on computers generating their own language as they want to solve some tasks together. So if we can imagine the computer would be able to create a language in this way, they might be able to understand language much better. What else we can combine speech and vision? Our language depends highly on how we see things. Almost every sentence that I said have at least some words that you can imagine how it looks. If I say to you a cucumber, you immediately imagine a cucumber. Computer don't have it at all. They don't have anything really good that combines speech and vision as a form of language understanding. We can also try to learn language by interacting with humans. How child learn language? They interact with their parents. Computers currently don't do it. They just take this huge corpus and try to memorize it without any interaction. And finally, we might want to create what is called the goal-based language model. Instead of just predicting the next word all the time, we might want to have a goal. We want to tell the computer, let's try to answer this specific task in the best way. And this would also might help him understand language and the purpose of language better. So these are many different approaches that some of them I hope might work, or as I said, maybe just increasing the size by 100 would help us. So to summarize this lecture, NLP is a very exciting field as it is advancing very rapidly in the last 2 years. Our computers, to answer the question in the title of the presentation, they cannot think yet, but they might already be in the right path. And as we said, a lot of things does hint to some sort of thinking of computer. Also, we see that you don't need to be an intelligent to perform intelligent tasks. We can take a pretty, let's say, dumb to some extent language model, and it can create a lot of fiction and answers a lot of questions in a very intelligent way without him being really intelligent. And this leads me to the last point. Even if we don't have an artificial general intelligence, even if we don't reach ever the phase of computers that are completely like human or even superhumans, the AI applications, and especially in NLP applications that we've seen and that are going to be developed in the next few years, have huge impact on us. They have impact on how we work. They will have impact on how we communicate with each other, and it might even have impact on how we think. So this is a very interesting field and to be aware of and to keep in mind. This has a lot of effect on our lives. Okay, so that's it. Thank you very much for your time and for whoever stayed up to this point. Vadim, you can turn off the recording, I think.